Today we are talking with Professor Henry Petroski, Professor of Engineering and History and author of To Forgive Design, Understanding Failure. Welcome to Readara.
Oh, thank you. It's good to be here.
Thank you. You have a fascinating book with the title To Forgive Design, Understanding Failure. Why design should be forgiven?
Well, there is a tendency whenever something happens, a broken bridge or a failed airplane, it's almost a knee-jerk reaction to say, well, it was a bad design, there was a design flaw, something about design. And when these accidents or failures are looked into more carefully, very often, not totally, but very often, it's not a design problem, but there's something else that the failure can be attributed to, such as human error. If it's an airplane crash, it can be pilot error, for example. And that really is pretty much the theme of the book, and hence the title. The title also harkens back to the title of my first book, which was To Engineer is Human, which is, an allusion to err is human, and to err is human, to forgive divine, so to forgive design. And it's a sort of a play on words from the Alexander Pope couplet.
The book has a very interesting, in a sense that you focus quite a bit on the bridges, and bridges become, generally they are also very fascinating to see, but certain engineering enterprises are also done in a way that they last much longer than people think they would. And obviously in those designs that last so long, there must be something done right there as well.
Generally, that's correct. Generally speaking, if something is going to fail, and if we're talking now about large structures like bridges or systems, the failures occur early. In part, that's because during construction or during test flights of an airplane, let's say, or during the filling of a dam, that's when the real test of the structure is the first big stress test, if you will. We saw with Obamacare, which is in the news lately, that its weaknesses showed up very early and became problematic. So although I write about bridges very much, I see bridges as metaphors for things generally, systems generally, and I don't mean the lessons learned from bridges to be taken literally.
No, that makes sense. Let's take a couple of examples that could highlight some certain examples that may have they kind of are fresh or vivid in the memories of common perception or understanding, and maybe we can work our way backwards in trying to understand why they were perceived that way as a failure, and then what really were the causes upon more closer introspection or more thoughtful analysis. Do you want to pick any one of the examples that you would feel more comfortable with? Do we want to go that far back as Titanic, or you want to pick Tacoma Narrows Bridge or a Minnesota incident?
Well, those are all good examples. Minnesota Bridge is interesting. You're referring to the one across the Mississippi on Interstate 35W, which collapsed suddenly in 2007. What's interesting about that case, and I like to try to select cases that have some interest and go against the conventional wisdom, let us say, that bridge stood for 40 years. So it's an example of something that didn't fail right away, but rather gave 40 years of successful service. It was, like all bridges, inspected regularly. That's another story we could talk about, is why are bridges required to be inspected every year or two, and that has to do with a failure, but that's a tangent. In the case of the Minnesota Bridge, it was inspected and given, the green light for years. But it turned out after the bridge collapsed that there were signs that it was weak, let's say, and it was a collapse could be considered imminent, but this was not taken seriously in large part because it wasn't reported in that context. It therefore involved human error. Now, this is a very interesting case because it was attributed to design, design that was inadequate. But again, this is a bridge that lasted 40 years. So just because a design is weak, let's say, doesn't mean that it necessarily follows that there's going to be a failure as soon as the bridge is constructed. Because engineering structures, especially, have built into them a certain, what's usually called a factor of safety, which in simple terms means that if you know this bridge is expected to carry so much traffic, which you can calculate weighs so much, well, then you design it to carry 2, 3, 4 times as much traffic and therefore weigh proportionately more. So the bridge has a reserve strength. Every structure has a reserve strength, and what that reserve strength is depends on the consequences of the failure that might occur. Where there is a more threatening failure that could kill more people, let's say, and ultimately that's the measure of what we want to avoid, then we make the structure much more safe in terms of factor of safety. It took a while to bring this out, as it does with most failures, because there are, at the beginning, when a failure occurs, a lot of competing explanations, some plausible, some less so. Eyewitness accounts are notoriously unreliable. People see what happened from different points of view. The National Transportation Safety Board is the organization in the United States that investigates failures of this type, and they sometimes appear to be slow in coming to a conclusion. But the reason is that they're trying to consider all of these alternative possibilities. And when they finally do announce a cause, if you will, of the failure, they often hedge even then, and they will say something like the most probable cause. Because, of course, it's hard to prove what really caused the failure in mathematical terms, if you will, in rigorous, mathematical terms, in the sense that you could prove it with theorems and numbers and so forth. And one of the reasons for that is if you have a hypothesis about a failure, how do you test that hypothesis? And that's the key idea in science and engineering, testing hypotheses. The hypothesis being that this is how the bridge failed. Well, how do you test it? The bridge is gone. Do you reconstruct the bridge exactly as it was? That's virtually impossible, because the bridge as constructed has certain flaws, some which may be known, some which may not be. And there's just generally no simple way to test the hypothesis.
Obviously, there are so many components, systems, engineering, construction goes into it, so obviously very difficult to recreate that.
Exactly.
And certain things are designed to fail, I think, as you talk in one of the chapters there. And that makes sense, because, if you have a car and you expect the car to last, engine to last 300,000-400,000 miles, and after that, you don't want that engine to work because it may not be as efficient in what it was designed to do. You want to expand on that why that is a key or important issue?
Well, certain things are designed to fail. It could be as simple as something like a pop-top can. If you have a can of soda or beer, when you pull on the tab, you want it to break. That's a failure. So there's a lot of design and engineering and metallurgy and special knowledge that goes into accomplishing that. You want this can to be able to contain all the pressure that is in a carbonated drink for possibly, months or years. But then when you want to drink it, you just want to be able to pull the tab and have the thing break or fail. So that's a designed-in failure that is for the good, we might say. Fuses, whether in a car or in a house, or circuit breakers, are designed to fail when they sense, too much voltage or current going through a circuit. These are good failures, you might say, because the consequences of them not happening could be a fire. But generally speaking, we tend to think about failure as something that's bad and undesirable. And one of the things I wanted to get across in this book is that that's not totally true all the time. That's why the subtitle is Understanding Failure. It's a very complicated concept, and it has, well, like so many things associated with human creation and human use, very many facets that make it not as simple as going from A to B to C in all cases when we try to reason what might happen or what had happened in retrospect.
It has the preventive measures built in, and that failure may lead to a prevention of a much larger failure. And that may be the nice way to look at it. There are different mechanisms of failure. Some of them are metallurgical, some of them are thermodynamics related, some of them are physics related. If you want to kind of sketch out what are, especially if you want to go back to the examples of the bridges. But then also you raise a very good point about Obamacare or any kind of program or system out there. Generally, where the failures lie, or where are the sources, or how far back we can trace the sources of failure.
Well, that's right, and I'm certainly not a specialist in legislation or medicine or Obamacare, but that was an embarrassment to the administration. It was attributed in part early on to the software for enrolling online and so forth. That was in the first few weeks and months what was pointed to as the reason it wasn't working. But as time evolved, and as we see in the current debates over repealing it and so forth, that there are failures of it that go more deeply, having to do with increased premiums, with problems of deductibles and so forth. This is an example then that fits what I was discussing earlier, that what seems to be the initial explanation is not necessarily the ultimate way of understanding what actually happened.
Why is that gap? Why people are quick to jump to the conclusion, and then we take some time to learn and understand, and it takes obviously some time because, as you say, if the bridge is broken, it's collapsed, it's gone, you cannot recreate it. So obviously we need a lot of data, we need a lot of information, we need lots of people who worked on it to go back and trace their memory and find documents to work back. But when we design, shouldn't we be building these things in place along the way so that if we do have a system like this, we can walk back or trace back, like in a lot of weapons or a lot of software engineering people? They've learned from all these things so that they have a lot more traceability.
Well, that's interesting. You bring up software people. Software building is not as old an activity as bridge building. When my first book came out, To Engineer is Human, which was about failure also, its subtitle was The Role of Failure in Successful Design. I was invited to talk quite a bit to software engineering groups. And the reason was that early on, they had very little history. They had very little accumulated experience, let's say. And they wanted to learn by analogy. They felt definitely that what they were doing was design. They were designing programs. They were designing software systems to accomplish a certain goal, a certain function. But they didn't have a great deal of experience in failures, in software that failed. So therefore, they felt that they didn't have the breadth of perspective on how to analyze failures. And they thought, well, bridges go back centuries, and there have always been failures of bridges, which is, in part because it's the nature of designing anything to have failures. Some people have said that if we have no failures, we're not trying hard enough to expand the technology or advance the technology. And in fact, if we're not having failures, if we're being overly conservative, we're not spending the resources of a society in a proper way because we're spending extra money on structures to make them super strong when in fact we could be using some of that money to be putting it toward, let's say, social programs or whatever have you. And, we see that in Washington debates all the time. When budget discussions come around, where do we put the emphasis? Where do we spend the money? If we increase this part of the budget, where do we decrease it? So the software people thought they might learn some from experience of bridges. Now, of course, after they've had decades, almost of the order of half a century of experience, they have their own experience. They have their own anthologies, if you will, of failure stories, horror stories, war stories, whatever you want to call them. So they don't have to appeal so much to analogy now. But in the beginning, they did. And that's a similar thing happened, actually, with engineering failures, structural engineering failures, like bridges. In the 19th century, the engineers looked to medicine as a possible source of guidance, let's say, in how to analyze failures, and they looked to medicine and to pathology. That the medical profession did autopsies and things like that to learn why people died or why they got sick, and that's what engineers would call a failure analysis. So every profession learns from other professions, but as a profession matures, it then believes that it has enough internal experience that it doesn't have to look outside so much, and sometimes that could be a limitation.
As time goes by, the technologies get more and more advanced, and our understanding of the technology and its application also improves, or at least supposed to improve. There are certain ways we analyze failures today than probably how we were analyzing them 10 or 20, 50 years ago, and how we should be analyzing failures. There's so much of sensing technology available that we can build in it, so that way we can make it as a live design and keep collecting the data, accumulating data along the way. So just like a flight recorder, there's always data available that we can constantly analyze. What I'm saying is the analysis, how the analysis of failure is done now, or in your vast experience, how we think we will end up doing as time goes by.
Well, you're correct. Things change in all technologies. And today, for example, we talked about the Minneapolis Bridge in Minnesota. When that bridge failed, a new one was, of course, built to replace it because it was such a vital link in the interstate highway system in the region. That new bridge, the replacement bridge, is what's called a smart bridge. It has a lot of sensors embedded in it, so that if, let's say, cracks develop in the concrete, which are a signal that things are not necessarily behaving the way they're expected to, that this could be immediately known. It won't be dependent on some human inspector visually looking at the bridge, let's say in a year or two. So this is really the future of the at least the bridge industry at the present. That these smart bridges, where there's a lot of remote sensing and wireless conveying of the data, even aspects, I would say, repairing the bridge in real time, such as concrete that will heal itself, so that if cracks develop, the concrete will actually begin to fuse back together over the cracks. This is a cutting-edge area of research. Everything, even something as old as bridge building, always has a frontier, and this is just the nature of technology. And if we were to talk in a half century or a century, long before we're probably gone, there will be things that maybe we can't even imagine today that will be involved in really trying to prevent failure. Some people define the object of engineering, the object of design, as to not have failure occur.
And that was actually leading to my next question. What is the obligation of an engineer?
Well, that's a good question, and that has a historical background too. The obligation of the engineer is actually a phrase that is part of a Canadian tradition, also known as the Iron Ring tradition, whereby engineers pledge to be ethical and to be hold very much in high in consciousness the safety of the public that is going to use their constructions, their designs. It's akin to the Hippocratic Oath of medical doctors. And it began back in the 1920s, so it's about a century old again, that term, because there were a lot of people claiming to be engineers in that era who didn't have any proper education or training. There were still apprenticeships, didn't have apprenticeships, and yet they were claiming to be able to design dams and bridges and so forth, and a lot of these were failing. There was a famous failure out in California called the St. Francis Dam failure that killed at least 400 people. The total death toll is still not known. It happened in the 1920s. And the so-called engineer who designed that dam had no real engineering credentials. So there was a movement in the early part of the 20th century to have engineers registered. And in the United States, that took the form of taking an exam, and before you could take the exam, you had to have a certain amount of experience. And then when you completed that period of experience and exam, you could call yourself a professional engineer or put the letters PE after your name. In the United States, this is regulated by the states the same way that medical doctors being able to practice or lawyers being able to practice have to, be registered, have to take bar exams or medical exams. The professions are really very much similar in that regard. So the obligation of the engineer is usually embedded in the codes of ethics that these professionals adhere to or attest to when they earn the right to put these special letters after the name, whether they be PE or MD or Esquire and so forth.
Just to keep things under control and make it more structured and make sure that the right person is doing the right job, at least from the regulatory perspective. Anything that we build has a budgetary implications, or there is a budget that is given to us or to a person or an engineer who is going to build something, and then there are certain expectations of that engineering or construction or building design, especially when the public projects are involved, like in the Boston Big Dig that seem to never end, or when you are sending out astronauts or a large space exploration ships over into space. There are politicians involved, there are lawyers involved, there are legal issues that become important down the line if there are private contractors involved as well. All these things just creates a greater chaos and more unpredictability and finger pointing and responsibility dispersion. In your experience, when you look at all these situations and certain things do go haywire and they become very expensive, what do you suggest that could have been done, or that should be a standard practice that could minimize? We cannot eliminate these things. All we can do is minimize them.
Oh yes, I agree. These are real problems. There is one thing that is happening in construction, especially of large structures like bridges, that is not totally new. It's something that has been around for decades. In Europe, for example, it's called Designbuild, and it is where the same engineering firm designs and builds the bridge, let's say. This is in contrast to the traditional way of doing it in the United States, where a state Department of Transportation, for example, might, through its analysis of traffic patterns and so forth, say, well, we need a new bridge here because the old bridge is wearing out or it's inadequate in its capacity. And then that Department of Transportation, if it's large enough, its engineers might design a bridge, or if not, they would hire outside consultants to design the bridge. Then they would probably, before or after, depending on the way it happens to be done in that particular state, get the authorization for spending the money to build such a bridge. Then they would advertise for bids, inviting construction companies to submit bids, which was often done anonymously in sealed envelopes. Then very ceremoniously, the envelopes would be opened, and in the simplest cases, the lowest bid, money-wise, would get the contract. And then they would proceed to build the bridge. If there were problems, if things didn't align or things didn't match up because the blueprints weren't exactly totally correct, there'd be finger pointing about whose fault it was, and that would consume time. It would introduce legal challenges, lawsuits, and that was what was attributed to for causing a lot of delays and cost escalations. This concept of design build is hopefully, and in many cases it does, eliminate a lot of these problems, because the same company, knowing that it's going to have to design and build the same project, doesn't want these conflicts, because it would be just fighting with itself, and that would just be eating into its profits. So there's a much greater care taken, and there's a recognition that, well, the designers should talk to the builders all along in the process so that there is a minimization, if not a complete elimination, of potential problems or failures, we could even say. The Minneapolis Bridge, which we've mentioned several times, the replacement bridge was built under precisely that kind of contract, design build, and the replacement bridge was built on budget but ahead of schedule, and it was a great relief to the people of Minneapolis and the area that it was done this way, because it restored regular traffic patterns. New York State wanted to build a replacement bridge for the Tappan Zee Bridge, which crosses the Hudson River north of New York City, and the state of New York wanted to use this design-build concept, but it was not allowed under New York state law. The governor of the state of New York promoted legislation that would allow it to be used, because he and his advisors obviously recognized the advantages of this. And this is happening in states around the country now. And I think we're going to see increasingly more of it. And generally speaking, it's believed that it ensures adherence to schedules and adherence to budgets, because one company involved, and you can't go and sue the designer or the builder if you feel you're getting the short end of the stick.
Yeah, very well said. We have been speaking with Professor Henry Petroski, author of To Forgive Design, Understanding Failure. In the book, you have a very nice backdrop and a little bit of backstory about the automotive safety features. What were the engineering challenges or political pressures under which the engineers had to work in order to get where we are, where obviously cars are much safer today than they were just 20, even 10 years ago?
Yes, that's a very interesting story. I wanted to make the book more than about bridges alone, so I have a few chapters like that. And Ralph Nader plays a big role in that chapter. In the 1950s, roughly, there were growing fatalities due to automobile accidents. After the war, automobile ownership and driving increased considerably. The number of deaths due to automobile accidents grew to, I think, over 50,000 a year, greater than it is now. Now it's down to about 35,000 a year, I believe, with more cars and more drivers. And it's due in large part, that decline to Ralph Nader and his book, Unsafe at Any Speed. And his book is actually very much about design and about safety and about failure concepts. In that book, he makes it clear that automobile designers were designing under the assumption that the cause of accidents was the driver. If a car went off the road and crashed, the driver was at fault, and whatever happened, it was the driver that was seen as the cause of the failure, not the design of the car. The design of the car was not seen as the main culprit. Well, Nader argued, and I think very persuasively, that if the design of the car were made with safety in mind more, so that even if the driver made a mistake or fell asleep or whatever happened, the car would be more forgiving. And he talked in quite much technical detail about, for example, the steering wheel. In cars in the early 1950s, the steering column was a very rigid piece of steel, so that if somebody driving the car like that had a head-on crash, the steering wheel would impale them, basically. He argued for collapsible steering wheels. Dashboards were largely, rigid pieces of steel covered with material that was just cosmetic. He argued for padded dashboards. Seatbelts were not mandatory at all. In fact, they weren't standard on cars. If you wanted a seatbelt in your car, you had to pay extra. It was considered, a safety package, if you will. Nader argued that it should be, standard. It should be incorporated into the car and into the price of the car, therefore. And he had a very profound effect on the design of cars through his book and through testimony before Congress. And a lot of what we have today, we have to attribute to him. And basically what he was doing was looking at what was the cause of the failures. And in this case, of course, the failures are ultimately the deaths of people in automobile accidents.
Very well said. Well, thank you very much for your time. And it's been a learning experience and enjoyable experience to listen to you as you describe. And now we have a different perspective on the failure. There are certain failures are good failures. They are by design, and certain failures are there, and we should use that as an opportunity to test the upper limits of engineering.
Well, thank you very much. It's been very interesting talking to you, too.
Thank you very much.